see, where are we? Okay, so this is going to be example 5. Okay, the van der Waals equation. You remember the van der Waals equation from general chemistry. It is a fix of the ideal gas law to bring it more in line with the description of the way real gases behave. So the van der Waals equation of state, and again, it's an equation of state because it gives you the state of a particular system. It is, I'm going to write it in this form, RT over V minus B minus A over V squared. Okay. Find dP, the total differential. Okay, well, let's be formal about this. P is a function of the variables t and v, right? So it's very, very important that you actually pick out your variables and know what your variables are, what your independent variables are. So in this case, r is a constant, b is a constant, so t and v are the only two variables. So p is a function of the two variables, t and v. Okay. Well, let's go ahead and take dP. Well, actually, let's write it as, let's write the individual. Let's go ahead and write the formula for the total differential. dP is equal to dP with respect to the first variable, holding the second variable constant, times the differential of the first variable, dt, plus the partial of the function with respect to the second variable, holding the first variable constant, times the differential of the second variable. Okay, now we just need to plug these in. We need to find, we have a function. We have the function right here. So once we actually have a function, we'll find the derivative of that function with respect to t. We'll find the derivative of that function with respect to v, and we'll just put them in there. We'll leave that alone, we'll leave that alone, and we'll leave that alone, and we'll have our actual total differential for a specific function, in this case, the van der Waals equation. Well, okay, let's go ahead and do it. Well, let's see. dP when I go ahead and differentiate this with holding v constant, so v doesn't matter, I end up with the following. I end up with r, again, I'm with respect to t, so it ends up being r over v minus b. That's dP dt. That's that one. Now let's go ahead and take the derivative with respect to v, holding t constant. The derivative of this holding, this time, t constant. What you end up with is the following. You end up with minus RT over V minus B squared minus a minus A times 2 times V over V to the fourth. And then when I go ahead and cancel, I'm left with my final expression, which is minus RT over V minus B squared. The minus becomes a plus, and it becomes plus 2A over V cubed. Well, now that I have this and this, I plug them in to here and here. And I have my final expression. The total differential of P is equal to R over V minus B squared times dt plus minus RT over V minus B squared. This one is squared, not this one. This one is squared, not this one. V minus B. It's going to happen a lot. Plus 2a over v cubed times dv. This is the total differential for the van der Waals equation. And again, it's all based on, given a function of two variables, the total change in that function when you vary both variables simultaneously is df dx holding y constant times the change in x that you make plus the derivative of the function with respect to y, the partial with respect to y, times the change in y that you make. That's it. So hopefully this has, for those of you that actually have a background in multivariable calculus, it's not a problem. A lot of this should be review. You may not have actually seen the total differential. Some multivariable classes talk about it, some don't. For those of you that have never seen partial derivatives or the total differential, I hope that this has actually made you feel a little bit more comfortable. So starting with the next lesson, we're going to jump right into thermodynamics. Till then, welcome back to Educator.com, and I'll see you next time. Bye-bye.